Hello there guys, and welcome back to another epic inexorable maths video. In this video we're doing something slightly different. We're not actually doing any A-level maths, which is the videos that I've been doing at the moment. We're looking at something else. Now this does tie into A-level maths. If you're doing A-level maths or A-level further maths, then this is definitely something that is worth knowing. Although most of it, if you're doing like further maths, should be revision sort of things. But if you're not doing A-level maths or A-level further maths, maybe you're doing GCSEs, maybe you're doing some sort of different qualification, in another country, or maybe you just want to learn. In this video, we're going to take a look at different sets of numbers. That's the best way to describe these types of numbers. So these are ways that we can group or categorize numbers together and describe them in helpful ways. And basically I've written some notes for every different type or set of number, and we're going to talk about 9 different sets of numbers, ranging from very, very easy and basic stuff to some quite complicated stuff. So if you do get lost at any point in the video, don't worry too much about it. So there are lots of different categories of numbers. The categories that you'll see in this video are not all of the categories of numbers. There are plenty of other numbers that we haven't I haven't written down, and we're not going to talk about in this video. Potentially though, we can in the future. And in this video we're going to look at some of the most important sets of numbers. So we are going to look at probably the most important categories of numbers. And without further ado, let's just get into it. Okay guys, so the first grouping of numbers, the first set of numbers, is the natural numbers. These are called natural numbers because they're the first numbers that early humans would have thought about. You know, if you have, let's say that there's 4 of you, you're all cavemen, and there's 1 mammoth. Okay, 4 cavemen, 1 mammoth, or there's 10 of us, how much food do we need? These are natural numbers. We're talking about the counting numbers here. So the natural numbers are denoted by this kind of thick N. That's what I like to call it. I don't really know the correct word for it, but this sort of fancy N shape that we've got coming on over here, that just means the set of natural numbers. And we write that as sort of some curly brackets, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up to infinity. So the natural numbers never stop. They continue all the way up to infinity, but they are only the positive whole numbers. And they are the counting numbers. That's how you can think of them. Some people consider 0 to be a natural number. Conventionally, it is not considered to be a natural number. Assume that it is not if it's not specified, but it should be specified. If you're dealing with a question or some sort of problem or statement, and it talks about natural numbers, hopefully it will specify whether it includes 0 or not, but normally it does not. Because when you count things, you don't go 0, 1, 2, you just go 1, 2, 3, right? You don't include 0 in the natural numbers conventionally. Some people do, so just look out for it, but in general, people don't. These are natural numbers, and they are the most basic forms of numbers. Okay, the second group of numbers that we're going to talk about today are the integers. The integers are the same as the natural numbers, but they always include 0, and also they include the negative whole numbers too. So it goes from negative infinity, negative 5, negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up to infinity on the positive end. So it's all of the whole numbers basically, positive, negative, and 0. And that's what the integers are. Again, these are the second sort of sets of numbers that you might learn about if you're in school or something like that. You learn about 1, 2, 3, 4, 5, then you learn about 0, and then maybe you're going to learn about some negative numbers. And then the next type of numbers that we're going to look at are the rational numbers. And the rational numbers, they're slightly more complicated to define, but guys, I think we can do it. It's not too much. And again, this is kind of the order that you go in if you're maybe in school and you're learning about maths. The next set of numbers that you might learn about are fractions, and that's what a rational number is. So we use the symbol thick Q to represent rational numbers. The reason why we use Q is because R is already taken. And you'll see that in a moment. So it's Q. I know it's a bit strange, it's Q. The reason why we use the letter Q for rational numbers is because Q stands for quotient. Quotient means fraction. And rational numbers, the definition of them are any numbers, positive, negative, 0, which can be represented by a quotient of 2 integers. That means a fraction of 2 integers. So that means that all integers and all natural numbers are rational. And we're actually going to take a look at some examples just to be really clear what we mean when we say what we say. Okay, so let's look at some examples. I'm going to write some down. Of course, there are too many to truly count, but these are some of the ones as an example. One example of a rational number is a half, 1 over 2, 0.5. That's a rational number because it is the fraction of two integers, 1 and 2. Likewise, minus 1 over 2 is also a rational number. That's minus a half, minus 1/2, just like that. The reason why that's a rational number is because minus 1 is also an integer, and 2 is an integer, so minus a half must be rational because it's the fraction of two integers. Another rational number is 0. The reason why 0 is a rational number is because we can write 0 as 0 over whatever we want. Choose any rational number, choose any integer rather, that you want, except 0, of course. 0 divided by 0, we can't do that. But let's just choose the basic one. Let's just choose 1. 0 divided by 1 is 0. 0 is an integer. 1 is an integer. That means that 0 over 1 must be a rational number, which means that 0 is a rational number. Another rational number is 40. Positive 40, that's a rational number. Because just like how we can write 0 as 0 over 1, we can write 40 as 40 over 1. 40 is an integer. 1's an integer. That means that 40 is rational. Negative 40 is another one. Negative 40 for the same reason. 36. 5 over 2. 7 over 3. 101 over 4. Any of these things, positive, negative, 0, these are all examples of rational numbers. They are the ratio, that's where it comes from, of two integers. Okay, so the next group of numbers that we're going to look at are the irrational numbers. These are the opposite of rational numbers. We use the simple thick P to represent irrational numbers, okay? And irrational numbers are numbers which cannot be represented as a fraction of two integers. So yes, they are the opposite of rationals. And we're going to look at some examples of irrational numbers now. So these irrational numbers, these are numbers which we cannot write as one integer divided by another integer. It's not possible to do that with these irrational numbers. Let's think of some irrational numbers here. One irrational number, potentially the most famous one, is pi. Pi cannot be written as a fraction of two integers. It's not possible to do that. Pi is an irrational number. Another very famous irrational number is the square root of 2. The number that multiplies by itself to make 2 is irrational. Minus the square root of 2 is also irrational for the same reason. We cannot write minus root 2 or minus pi for that matter or anything like that as the ratio of two integers. It's not possible. Another irrational number is the number e, Euler's number. If you've ever heard of this number, it's roughly 2.718. It is irrational. The square root of 3 is irrational. The square root of 5 is irrational. The square root of 10 is irrational. The cube root of 2 is irrational. Let's say minus the fifth root of 14, why not, is irrational. All of these are irrational numbers, and they cannot be represented as a quotient or fraction of two integers. Okay, the next group of numbers that we're going to talk about are the real numbers, and this is where the R comes from. This is why rational numbers can't be used with a thick R. Real numbers have already taken thick R. So real numbers use the symbol thick R, and that symbol represents the real numbers. Real numbers are numbers which lie somewhere on the real number line. So all that means is, imagine a number line, like in a classroom, maybe it's sort of, on the wall. It's, it goes from 0 and it, maybe it counts to like 10 or 20 or something like that. Imagine that the number line went all the way up to infinity. And also, some number lines, they also have negative numbers on them, don't they? So, they go -1, -2. Imagine it went all the way to negative infinity in that direction too. So it's like basically an infinitely long line with 0 in the middle. If the number would be somewhere on that number line, then it is a real number. And of course it is. So real numbers, there are plenty of them. All natural numbers, integers, rationals, and irrational numbers are real. Of course they are. They're real numbers. Don't confuse it. Don't make it too complicated. Every number that we've spoken about, of course, it's a real number. Of course, it is. And you'll realise in a moment why we're talking about real numbers. Isn't every number a real number? No. And we're going to find out why in a second. But for now, let's look at some real numbers. An example of a real number: 2. 2 is a real number. 1. 1 is a real number. 0. Pi. Pi, of course, is a real number. Pi minus 5. Why not? 5 over 2. Pi squared. Why not? Any number like this, we can say the square root of 3 minus 50. These are all real numbers. They're all numbers which would appear somewhere on a number line. Now, it might be really hard to find them, like, how are you actually going to get pi on a number line? Like, where, you have to zoom in. But it's somewhere, right? The pi is somewhere on the number line, It's in between 3 and 4. It's somewhere on there. But we're going to talk about in a second numbers which are nowhere on this number line. They do not exist on this number line. And that's quite exciting. So, the next group of numbers, these are numbers which are not real. These are the imaginary numbers. You may have heard of them before. You may have studied them before. But we're going to assume that no one's even heard of them. We're going to start from scratch. The imaginary numbers are interesting. So there's no agreed symbol for imaginary numbers, but the common ones that are used are thick I, which just stands for imaginary, and lowercase I times thick R. And you'll see why in just a second. So thick I, that makes sense, right? It just stands for imaginary. But what about lowercase I times thick R? Why are we using like a lowercase I times the real numbers? Like what's going on there? We're about to find out, we're about to see. So imaginary numbers are numbers which are in the form a times I, but we need to specify what a and I are. A is a real number. It can be any of the numbers that we have mentioned previously, but I is not. I is called an imaginary number, and I is the square root of minus 1. The square root of minus 1 does not appear anywhere on the real number line. Why? Well, what is the square root of minus 1? The square root of minus 1, what does that actually mean? That means the number that multiplies by itself to make minus 1. Just like how, let's say, the square root of 5 is the number that multiplies by itself to make 5. The square root of minus 1 is a number that multiplies by itself to make minus 1. But there is a problem with that. Think about this. Think about any positive number. If you square it, if you multiply it by itself, it gives back another positive number. For example, 3 squared. 3 squared is positive 9. But consider a negative number. Let's say minus 3 squared. Minus 3 squared is not minus 9, it's positive 9 again, because it's two negative numbers multiplying together to make a positive. So if you square any number, positive, negative, or 0, it will never be negative. 0 squared is just 0, a negative squared is positive, a positive squared is positive. Which means that you cannot take the square root of a negative number and it be real. You can't, it's not possible. So we say that I just stands for imaginary, is equal to the square root of minus 1. So this is not a real number, this is an imaginary number, okay? And a is just a multiple of that special imaginary number. So we could have, let's look at some examples here. We can talk about any multiple we want of I, or of the square root of minus 1. So for example, imaginary numbers. I, that's the square root of minus 1, that's an imaginary number. Another one is 2i. 2, that's the a. 2 is the a. That, a is any real number. 2 is a real number, so it's just 2 times I. 3i. 3i is also imaginary. Pi times I is imaginary. In fact, these numbers are any of the numbers that we've already mentioned, but just with an I on the end, just being multiplied by I afterwards. It's the a, where a is a real number, times I. And that is where this notation that we've got up here, this kind of IR comes from, okay? It's a real number times I, which is the square root of minus 1. These are the imaginary numbers, okay? Very cool. The next group of numbers are the complex numbers. And the complex numbers, the best way to describe them, they're a combination of real numbers and imaginaries, okay? And we're going to talk about that in more detail now. So we use the symbol thick C, because the C stands for complex. That represents complex numbers. Complex numbers are always in the form A plus BI. A and B are real numbers again. They are numbers which appear on the number line. And once again, I is the square root of -1. Okay, so all real numbers and all imaginary numbers are complex, okay? Because complex numbers encompass all of the reals and imaginaries and any combination of both of them. The complex numbers are basically all of the numbers. All of the numbers that exist are complex as far as we're concerned at the moment. There technically are other groups of numbers that we're not talking about, quaternions for example, but don't worry about those guys. Consider complex numbers to be any number, real, imaginary, or a bit of both. Okay, so complex numbers and imaginary numbers may seem silly or useless, but it turns out they're very important. And I've also written here, very cool, and they are very cool. Complex numbers are incredibly important. And it's true, you might seem, well, you know, why we complex numbers, we just made them up. Imaginary numbers, they're literally imaginary, we made them up. Why are we even studying them? It's silly, it's goofy, but actually they're really, really, really helpful. And the word imaginary, many mathematicians don't like using imaginary numbers because it doesn't represent what they are. Imaginary numbers, they don't work in the same way that we consider normal numbers or real numbers to work, but they very much are real in another sense. And that's in the sense that they do help us solve real world problems, despite not working in the same way that normal numbers do. So the reason why we write them in A plus BI form, and the reason why we can say that all real numbers are complex and all imaginary numbers are complex, is because if we consider A plus BI, where A and B are reals, if we want an imaginary number, remember our imaginary numbers, let's look at some imaginary numbers. These are also examples of complexes. So let's say like 3i. Well, 3i is the same thing as 0 plus 3i. That's A plus BI. A is 0, B is 3. Complex. Let's consider a number, imaginary number. Let's say pi times I. That's the same thing as 0 plus pi I. Again, A is 0, pi is B is pi. That's a complex number, A plus BI. Let's consider some real numbers. Let's consider the number square root of 5. This is also a complex number because we can write the square root of 5 as the square root of 5 plus 0i, where A is the square root of 5 and B is just 0. We can also say that, let's say, 7 is also a complex number because 7 is 7 plus 0i, A plus BI. But we can also get combinations of both. So for example, 1 plus I. 1 plus I is a complex number. We can't simplify that. That's just how it is. That's how it's written, 1 plus I. Another one is, let's say, 2 minus the square root of 3 times I. That's a complex number. It's a combination of both. We can say 5 over 2 minus 4/3 of I. This is a complex number. So it's any combination of real and imaginary components, and the only rule is that A and B have to be real numbers. Okay, so this is where things get a little bit trickier. Okay, so these are algebraic numbers. The definition of an algebraic number is much harder to define than all of the others. Okay, so if you're lost here, don't worry too much about it. I'm going to try my best to explain it. You will need to know a little bit more maths to get this one. So, algebraic numbers. We use the symbol thick A or thick Q with a line on top of it to represent the algebraic numbers. You might think an algebraic number is like an X or a Y. It's not. They're different. They're not like, they're not symbols. They're numbers, but we're going to talk about what they are. So, algebraic numbers, this is the definition, are any number. They can be real or complex. That basically just means complex, but I've written real or complex. They can be any number that are the roots of a polynomial with a finite number of terms and rational coefficients. Okay, it's a bit of a mouthful, but that's what they are. So let's break this down. What does this mean? Okay, so basically, imagine you have a quadratic equation. It's equal to 0, and you solve it. As long as those are written in the form ax squared plus bx plus c. As long as a, b, and c are rational numbers, if you solve it for x, the answer is always algebraic. That's the definition of an algebraic number. It's a number which is the solution to a polynomial equation. But it's not just quadratics. It's any order polynomial. So cubics, quartics, quintics, and the list goes on. It's any. As long as there's not an infinite number of polynomial terms. So you can't have, like, if you know what a Taylor series is, those don't count. It must be finite. So, maybe the highest number is, an x to the 20, or an x to the 300, or an x to the 3 billion. As long as it just doesn't go up to infinity, that's an algebraic number. If it is the root of that equation, and all of the coefficients in front of those x to the power of whatevers, they must be rational numbers. You can't have pi x squared minus 2 pi plus pi equals 0 or something. You can't have that, because pi is not a rational number. Okay, so let's look at an example, because I don't want anyone to get confused. So, for example, the square root of 2 is a solution to the polynomial equation x squared minus 2 equals 0. I hope we agree with that, because if you substitute x equals 2 into this equation, you do get the square root of 2 squared, because this is the x squared here, minus 2 equals 0. This is definitely true, because the square root of 2 squared is 2. 2 minus 2 equals 0. That's definitely the case. We all agree, I hope. That means that the square root of 2 must be algebraic, because it can be the solution to that equation. Another example of an algebraic number is minus the square root of 2, for the same reason, because negative root 2 is also a solution to that very equation. The square root of 3 times I is also algebraic, because if you know anything about complex numbers, you'll know that the square root of 3i squared is minus 3. Plus 3, that's 0. So the square root of 3i must also be algebraic. And also minus root 3i is algebraic too. So these are quite a lot of numbers. In fact, all natural numbers and integers and rational numbers are algebraic. Some irrational numbers are, so the square root of 2, that's definitely algebraic, but not all of them. Let's look at some algebraic numbers very quickly. So, an example of an algebraic number. 4. 4 is an algebraic number. 4 can be the solution to a polynomial equation. Of course it can. 3. 5 over 2. A third. These are all algebraic. The square root of 2. Oh, that is not really a 2. The square root of 2. The cube root of 4. These are all algebraic. I, the square root of minus 1. The square root of 2 times I. Minus I. Why not? And we'll even say minus I plus 5. Normally you'd write that as 5 minus I, but we're going to be crazy. These are all algebraic numbers. And you might think, oh, what about like pi? Is pi algebraic? No. No, pi is the last category here. We're going to talk about the next category of numbers, the last category, and that's going to be transcendental numbers. Okay guys, this is our last group of numbers. It is the transcendentals. So what is a transcendental number? It's the opposite of an algebraic one. So the transcendental numbers, there's no agreed symbol for these guys again, but the most commonly used one is the complex numbers minus the algebraic numbers. That's because the transcendentals are any number, it's any complex number that includes the reals, imaginaries, or the actual complexes, like the a mixture of both, but not the algebraics. So it's all of the complexes, but not the algebraic ones, because they're the opposite of algebraics. That's why. Transcendental numbers are numbers which are not algebraic. I've already mentioned that. That's good. Therefore, transcendental numbers cannot be roots of a polynomial with finite terms and rational coefficients. This is stuff we've already covered. It's just the opposite of algebraics again. They are not ever the solutions to a polynomial equation with finite terms, rational coefficients. It's a bit of a weird one to get your head around, but that's what they are. And this is quite fascinating, I think. The vast majority of all numbers are transcendental. Think of a number. Now, you're probably going to think of something pretty rational, or maybe thought of like pi. But that's because we don't know many transcendentals. But if you actually just had, some magical way of just grouping all of the numbers that ever exist together and reaching into this bag full of, this fictional bag of numbers and just, sort of taking them out and putting them into two groups, transcendentals and algebraics. Take a transcendental out, take an algebraic out, and maybe you've got like a bowl, right? This is all hypothetical. You've got like a big container and you're going to put all of your transcendentals in one, all of your algebraics in the other. You might think, well, there's way more algebraics. Actually, it turns out there's not. Almost every number is transcendental. We just don't know about many of them because they're really hard to find. They're very, very hard to prove, How do you prove that a number is transcendental? It's difficult. It's very hard. We have proved some of them are transcendental, though, and there's some very famous guys that we're about to look at in a second. We only know about a small fraction of the transcendental numbers, but we do know that most numbers are transcendental, which is very strange, but it's true. All transcendental numbers are irrational, okay? You cannot have a rational transcendental number. Why? Because all rational numbers are algebraic, so they're all taken by the algebraics who are very greedy. Okay, so let's look at some examples of transcendental numbers. The most famous transcendental number, whether people know that it's transcendental or not, is without a doubt pi. So pi is irrational, it's also transcendental, okay? Pi is a transcendental number. It is never, ever, ever going to be the solution to a polynomial equation with a finite number of terms and rational coefficients. Never, ever, ever. No, can't be. That's an irrational. That's a transcendental as well. Another very, 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 very famous transcendental number is E. E is a transcendental number. Okay, again, same thing. Cannot be the solution to a polynomial equation like that. Okay. There are plenty of other transcendental numbers that we do know about. For example, e to the power of a, where a has to be an integer, it has to be a whole number, but not zero. Okay, so a not zero and a, we write it as a is an element of the integers, just like that. I was about to write a plus sign, but it doesn't need to be a plus sign. So this just, it looks really fancy. All I've written is e, which is a number, 2.718, and so on, to the power of any whole number, but not zero. That's always transcendental. So, for example, e squared is transcendental. E to the power of minus 1, that's just 1 over e. That's transcendental. E to the power of 100, that's transcendental, and so on and so forth, okay? One number that I believe is not proven to be transcendental, but generally thought to be, is e to the power of pi. We do not know if it's transcendental, I think. If anyone in the comments knows, definitely let me know. This is a number that is not, as far as I know, has not been proven to be transcendental, but is thought to be. Another number that is definitely transcendental is actually I to the power of I. The reason why this is transcendental is for a slightly more complicated reason, but it actually turns out, this is also quite interesting. It turns out that I to the power of I can be written as e to the power of minus pi over 2. Okay. Now I to the I has actually got an infinite number of values. And again, it's complicated reasoning, but the principal value, we call it, is e to the power of minus pi on 2. This is definitely a transcendental number. So we definitely know that e to the minus pi on 2 is transcendental. And there are plenty more. For example, we can do, the natural log of 2, that's transcendental as well. The natural log of 3. In fact, the natural log of any integer, except the natural log of 1, is transcendental. And there are plenty more, as I say. But these, it's generally things that are based around pi and e, and there are others that have nothing to do with pi and e, for sure. but the most famous ones are the ones that are related to pi and e. These are the transcendental numbers. Okay guys, that's all of our groups of numbers that we've got today, and that is the end. If you enjoyed the video, please let me know. Like, subscribe, share with your friends and family, tell them all about transcendental numbers and other groups of numbers, and I will see you guys in the next video. Cheers.